In mathematics, a Diophantine equation is a polynomial equation, usually in two or more unknowns, such that only the integer solutions are sought or studied. A linear Diophantine equation is an equation between two sums of monomials of degree 0 or 1. An exponential Diophantine equation is one in which exponents on terms can be unknowns. Diophantine problems have fewer equations than unknown variables and involve finding integers that work correctly for all equations. In more technical language, they define an algebraic curve, algebraic surface, or more general object, and ask about the lattice points on it. The word Diophantine refers to the Hellenistic mathematician of the 3rd century, Diophantus of Alexandria, who made a study of such equations and was one of the first mathematicians to introduce symbolism into algebra. The mathematical study of Diophantine problems that Diophantus initiated is now called Diophantine analysis. While individual equations present a kind of puzzle and have been considered throughout history, the formulation of general theories of Diophantine equations was an achievement of the 20th century. Examples: in the following Diophantine equations, w, x, y, and z, the unknowns and the other letters are given constants. Linear Diophantine equations. One equation. The simplest linear Diophantine equation takes the form x plus b equals c, where a, b and c are given integers. The solutions are completely described by the following theorem. This Diophantine equation has a solution if and only if C is a multiple of the greatest common divisor of A and B. Moreover, if is a solution, then the other solutions have the form, where K is an arbitrary integer, and A, U and V are the quotients of A and B by the greatest common divisor of A and B. Proof: if D is this greatest common divisor, B's outside entity asserts the existence of integers E and F such that A plus BF equals D. If C is a multiple of D, then C equals DH for some integer h, and is a solution. On the other hand, for every pair of integers x and y, the greatest common divisor D of A and B divides x plus b. Thus, if the equation has a solution, then C must be a multiple of D. If A equals UD and B equals VD, then for every solution, we have A plus B equals x plus b plus K equals x plus b plus K equals x plus b, showing that is another solution. Finally, give on two solutions such that x1 plus by1 equals x2 plus by2 equals c, one deduces that u plus v equals 0. As u and v are coprime, Euclid's lemma shows that there exists an integer k such that x2 minus x1 equals kv and y2 minus y1 equals minus q. Therefore x2 equals x1 plus kv and y2 equals y1 q, which completes the proof. Chinese remainder theorem. The Chinese remainder theorem describes an important class of linear, Diophantine systems of equations. Let n1, nk be k-pairwise coprime integers greater than 1, a1, ac be k arbitrary integers, and n be the product n1 and k. The Chinese remainder theorem asserts that the following linear Diophantine system has exactly one solution such that 0x less than n, and that the other solutions are obtained by adding to x a multiple of n. System of linear Diophantine equations. More generally, every system of linear Diophantine equations may be solved by computing the Smith normal form of its matrix, in a way that is similar to the use of the reduced row echelon form to solve a system of linear equations over a field. Using matrix notation, every system of linear Diophantine equations may be written in Ax equals C, where A is an m times n matrix of integers, X is an n times 1 column matrix of unknowns, and C is an m times 1 column matrix of integers. The computation of the Smith normal form of 8 provides two unimodular matrices U and V of respective dimensions m times m and n times n. such that the matrix B equals by J equals UAV is such that by I is not 0 for I not greater than some integer k, and all the other entries are 0. The system to be solved may thus be rewritten as B equals UC, calling ye the entries of E minus 1x and I those of D equals UC. This leads to the system by I ye equals die for 1 I k, 0 ye equals die for chi less than IN. This system is equivalent to the given one in the following sense. A column matrix of integers x is a solution of the given system if and only if x equals Vy for some column matrix of integers y such that by E equals D. It follows that the system has a solution if and only if by I divides die for ik and I equals 0 for I greater than k. If this condition is fulfilled, the solutions of the given system are where hk plus 1, hn are arbitrary integers. Hermite normal form may also be used for solving systems of linear Diophantine equations. However, Hermite normal form does not directly provide the solutions. To get the solutions from the Hermite normal form, one has to successively solve several linear equations. Nevertheless, Richard Zippel wrote that the Smith normal form is somewhat more than is actually needed to solve linear Diophantine equations. Instead of reducing the equation to diagonal form, we only need to make it triangular, which is called the Hermite normal form. The Hermite normal form is substantially easier to compute than the Smith normal form. Integer linear programming amounts to finding some integer solutions of linear systems that include also inequations. Thus, systems of linear Diophantine equations are basic in this context, and textbooks on integer programming usually have a treatment of systems of linear Diophantine equations. Diophantine analysis. Typical questions. The questions asked in Diophantine analysis include: are there ever solutions? Are there ever solutions beyond some that are easily found by inspection? Are there finitely or infinitely many solutions? Can all solutions be found in theory? Can one in practice compute a full list of solutions? These traditional problems often lay unsolved for centuries, and mathematicians gradually came to understand their depth, rather than treat them as puzzles. Typical problem: the given information is that a father's age is 1 less than twice that of his son, and that the digits ab making up the father's age are reversed in the son's age. This leads to the equation 10a plus b equals 2 minus 1, thus 19b minus 8a equals 1. Inspection gives the result a equals 7, b equals 3, and thus ab equals 73 years and bar equals 37 years. One may easily show that there is not any other solution with a and b positive integers less than 10. 17th and 18th centuries. In 1637, Pierre de Fermat scribbled on the margin of his copy of Arithmetica: it is impossible to separate a cube into 2 cubes, or a fourth power into 2 fourth powers, or in general, any power higher than the second into 2 like powers. Stated in more modern language, the equation n plus bn equals cn has no solutions for any n higher than 2, and then he wrote, intriguingly, I have discovered a truly marvelous proof of this proposition, which this margin is too narrow to contain. Such a proof eluded mathematicians for centuries, however, and as such his statement became famous as Fermat's last theorem. It wasn't until 1995 that it was proven by the British mathematician Andrew Wiles. In 1657, Fermat attempted to solve the Diophantine equation 61 by 2 plus 1 equals y2. The equation was eventually solved by Euler in the early 18th century, who also solved a number of other Diophantine equations. The smallest solution of this equation in positive integers is x equals 226,153,980, y equals 1,766,319,049. Hilbert's 10th problem in 1900, in recognition of their depth. David Hilbert proposed the solvability of all Diophantine problems as the 10th of his celebrated problems. In 1970, a novel result in mathematical logic, known as Martiusiewicz's theorem, settled the problem negatively. In general, Diophantine problems are unsolvable. Diophantine geometry, which is the application of techniques from algebraic geometry in this field, has continued to grow as a result. Since treating arbitrary equations is a dead end, attention turns to equations that also have a geometric meaning. The central idea of Diophantine geometry is that of a rational point, namely a solution to a polynomial equation or a system of polynomial equations, which is a vector in a prescribed field K, when K is not algebraically closed. Modern research, one of the few general approaches, is through the Hasse principle. Infinite descent is the traditional method, and has been pushed a long way. The depth of the study of general Diophantine equations is shown by the characterization of Diophantine sets as equivalently described as recursively enumerable. In other words, the general problem of Diophantine analysis is blessed or cursed with universality, and in any case is not something that will be solved except by re-expressing it in other terms. The field of Diophantine approximation deals with the cases of Diophantine inequalities. Here variables are still supposed to be integral, but some coefficients may be irrational numbers, and the equality sign is replaced by upper and lower bounds. The most celebrated single question in the field, the conjecture known as Fermat's last theorem, was solved by Andrew Wiles, but using tools from algebraic geometry developed during the last century rather than within number theory where the conjecture was originally formulated. Other major results, such as Faulting's theorem, have disposed of old conjectures. Infinite Diophantine equations. An example of an infinite Diophantine equation is n equals a2 plus 2b2 plus 3c2 plus 4d2 plus 5e2 plus, which can be expressed as, how many ways can a given integer n be written as the sum of a square plus twice a square plus thrice a square, and so on. The number of ways this can be done for each n forms an integer sequence. Infinite Diophantine equations are related to theta functions and infinite-dimensional lattices. This equation always has a solution for any positive n. Compare this to n equals a2 plus 4b2 plus 9c2 plus 16d2 plus 25e2 plus, which does not always have a solution for positive n. Exponential Diophantine equations. If a Diophantine equation has as an additional variable or variables occurring as exponents, it is an exponential Diophantine equation. Examples include the Ramanujan-Nagel equation, 2n-7 equals x2, and the equation of the Fermat-Catalan conjecture and Beal's conjecture, am plus bn equals ck, with inequality restrictions on the exponents. A general theory for such equations is not available. Particular cases such as Catalan's conjecture have been tackled. However, the majority are solved via ad hoc methods such as Stormer's theorem or even trial and error.